The final topic I want to discuss for Unit 0 is a topic that I always feel like I say too much about, but then I never seem to be able to shorten what I'm talking about for it. Uh, some aspects of what I'm talking about are not, too terribly important for later on in the year, but some of the things that I'm really going to go into detail on actually are very important for understanding how scientists think about data, especially how physicists think about data, and how they use data as a means to come to an understanding about how the universe works. So you'll kind of have to bear with me. You've so far survived my previous videos, which I'm sure you've already found to be a little bit wordy, and you'll just have to survive one more of these videos for this unit. So in this video, I'm going to be talking about data handling. In other words, basically how you organize data as you collect it, as well as some common ways that that data is then displayed to make it easier to understand. So for data handling, there's really three different ways to go about handling data. The two I'm going to talk about are data table and spreadsheet. And those are the two I'm going to talk about in more detail, but I would like to point out that these two ways of handling data are actually not the most popular way that students handle data. And I don't mean this specifically as a criticism of this year's students. I hardly know you yet. You could be a different breed than anyone else I've seen before. I'm speaking as much as anything about myself as a student here. And the most popular way that I see as a means of collecting data is the hodgepodge scatter, where basically you don't take any time to really think about how you're going to organize your data as you collect it. As you make a measurement, you just quickly scribble it on a piece of paper in the margin of the directions for the lab sheet or just wherever's convenient. And then as you run the experiment and you realize you need more measurements, you just kind of keep listing these measurements wherever is convenient at that moment. And that hodgepodge random spread is really, really quick for collecting data. But if you don't write that lab report within the next 20 minutes, those numbers stop making sense very, very quickly because there's no logic to how you've collected that data. So we want to avoid doing that anytime we're doing data collection, and we want to make sure that we're using one of these following two methods. And honestly, you're probably most likely going to be using the data table most of the time. So a data table is simply taking the experiment that you're going to do and thinking about what are the key elements of data that need to be measured for each trial, and then creating rows and columns to organize those measurements in a way that makes logical sense. The rows usually represent the trials that you're conducting, and the columns represent the measurement or measurements that are important for those trials. And so basically a data table is just a means of organizing your data into columns and rows that have labels and that make logical sense. It's pretty quick to do. Honestly, it's almost as quick to do a data table as the hodgepodge scatter approach. And it's very easy to kind of understand the organization. Where data tables kind of fall short is if you're conducting an experiment that requires many, many trials, and also requires that with each of those trials, you perform a calculation. In this case, a handwritten data table becomes very cumbersome to use. So it's just not a good payoff if you've got a very large data set that you're working with. The other way that data is organized specifically is created and implemented to take care of the main con of the data table. And this is a spreadsheet. A spreadsheet is basically an electronic data table. But what it does is it allows you to automatically calculate values from your data. So you can calculate in-between step computations for each trial individually, and you can also aggregate the results of all your trials together all at once. For example, taking the average of all of the length measurements for a particular experiment, or an average of all the time measurements for a particular experiment, or whatever it is. So you can both do calculations by row or aggregate calculations for an entire column at once. And the spreadsheet does this automatically. So the big pro for using a spreadsheet is that it can handle these large data sets where you wouldn't want to have to do every single calculation by hand, or even type it into your calculator for every single calculation. The reason many students never bother with spreadsheets, however, is that it takes time to learn how to use a spreadsheet program, and it takes time, even when you know what you're doing, to set the spreadsheet up. A data table, in contrast, is just so easy to draw a couple of vertical lines and horizontal lines on a piece of paper, and you've got your data table ready to go, basically. Kind of the deciding point between a spreadsheet and data tables usually comes somewhere around, are you doing less than 20 trials or more than 20 trials? For our physics class, it would be very rare. There may be a couple of experiments where it would benefit for you to do more trials, but for the most part, you're going to be doing 5 trials for any measurement that you're doing. There may be some cases where you might even get up to 15, but you're really never going to go above the number of trials and above the number of calculations where a spreadsheet really pays off in terms of efficiency. So you don't need to learn to use a spreadsheet, but I just want to point out that real scientists that have to handle large amounts of data, they do have to learn how to use spreadsheets. So if you plan on going into science or engineering as a field, this is a skill you do want to develop. You want to understand how something like Microsoft Excel works or Google Sheets works, and actually use formulas in it, not just enter numbers and labels into boxes, but actually learn how to make formulas work and calculate things for you, because that's where the power of a spreadsheet truly comes from. All right, so we just finished collecting our data, probably in a data table. And now it's time to think about how we're going to display that data so that it's easy for other people to understand the results of our experiment, perhaps even easier for us to understand the results of our experiment. Because while data tables are logical in terms of how they organize measurements, they don't really show relationships very well. And so this is where we get to 3 common ways that data gets displayed. And starting with the one over to the right on your note sheet, I can simply take my measurements for each trial and I can draw lines connecting all those dots together. And this is a line graph, right? The key thing is, though, that a line graph can't just be used arbitrarily for any data point or data set. It only makes sense for certain data sets where there's definitely a cause-effect relationship that exists between what is being measured on the horizontal axis and what is being measured on the vertical axis. And having that relationship between those quantities is essential. That cause-effect relationship simply is essential. And if I use a line graph, I'm claiming that a cause-effect relationship absolutely exists between these 2 axes. In comparison, if I have a data set where there is no cause-effect relationship, I'm probably going to be displaying that data in something like a bar chart or a histogram. Technically, those two words do mean slightly different things. So, don't start running around saying that they're complete synonyms for each other, but the output kind of looks the same. Whether you're dealing with a histogram or a bar chart, you're going to see bars that represent categories of results. So all the results that fall within one category build up to make a particular bar. The key thing here is that when I'm using a bar chart or a histogram, I'm specifically claiming that there really is not a cause-effect relationship, or I'm not confident that there's a cause-effect relationship between my horizontal and my vertical axis. And then the final way of displaying data that I'm going to talk about is a pie chart. And the pie chart is kind of similar to the bar chart, except for one crucial difference. And this is that I am confident that the different categories of data that I am collecting actually represent 100% of all of the choices that are available. So that if I've collected, once I'm done drawing my pie chart and I've allocated numbers to every single wedge, those wedges add up to 100% of the possibilities available in the universe. So we're going to take a look at some scenarios here where I might use one display type or another display type, and some things to be careful of as I'm using them. So the first data set that I'm going to list here deals with answering the question, what is your favorite color? So favorite color. So I go out, I ask a bunch of people this question, and I end up with the result that a certain number of people chose red, a certain number of people chose blue, and a certain number of people chose green. I only offered 3 choices, okay? And when I conducted this poll, I found that 4 people chose red. I discovered that 8 people chose blue, and I discovered that 2 people chose green. Okay. So you'll notice I've drawn this as a bar graph. And in doing so, I'm claiming that there's really no connection between the different categories of data. Now, if I were to use a graphing program for my data, I could probably force the computer to turn this data into a line graph. It wouldn't be correct to do that, but I could do that. And so the red marks I'm putting here are marks that are not true. So I can see the line goes up and then it goes down again, okay? But if I decide to display my data set of 4, 8, and 2 as a line graph, then what am I claiming is true about the data? Well, what I'm claiming is that there is a connection between color and people picking that color as their favorite, and that relationship exists for the values that exist in between 2 colors. So for example, what this line graph is stating is that because in my survey, 4 people were surveyed to like red and 8 people were surveyed to like blue, therefore I can conclude that 6 people would choose the color purple if it was offered on my survey. So let's say that again. Because I drew a line, I am claiming that all of these in-between points are valid measurements. And because purple is halfway between being red and being blue, having data about red and having data about blue allows me to make a conclusion about how many people would like purple. Now, hopefully you're realizing this is a pretty ridiculous conclusion to come to, but this is the conclusion I would be forced to draw if I decided to use a line graph, because a line graph claims there is a relationship between the horizontal and the vertical axes of your data display. Favorite color, that just doesn't make sense. So it's not correct to use a line graph here. Let's take a look at something different. Let's say I have a question about leg length. And my top running speed. And I go and I collect some data. And this is totally made up, so don't quote me on any of these numbers. This is just for illustrative purposes. But I discover that I test someone who has 80 centimeter legs. And I discover that they have a top speed of 4 meters per second. Boom. I then test someone with 90 centimeter legs, and I discover that they have a top speed of 6 meters per second. And I test someone with 100 centimeter legs, so a very tall person here. And I discover that they have a top speed of 7 meters per second. Maybe even I found, 5 people with 100 centimeter legs and 7 was the average. And I found 5 people with 90 centimeter legs and 6 was the average. And I found 5 people with 80 centimeter legs and 4 was the average. So each of these data points, I'm pretty confident that they're representative of people with that leg length, okay? How would I display this data? Well, the answer is, in this case, I absolutely would connect the data together with a line. And the reason that I would do that is, even though I only collected data for 3 leg lengths and really carefully measured people that had 3 different types of legs, if you were to ask me, okay, that's an interesting experiment, but my legs are 85 centimeters long, how fast would you expect me to be able to run? I would take a look at my graph and I would say, well, 85 is kind of between 80 and 90. And on the curve that my graph is making, that means I would expect you to run roughly 5 meters per second as your top speed. A shade more because there's a curve to this line. And I would draw that conclusion. So does that make sense? Well, in this case, remember, a line graph is claiming that there is a cause-effect relationship between what's happening on my horizontal axis and what's happening on my vertical axis. So does it make sense that leg length can cause a person to run faster or slower? Yeah, it does make sense, right? Because bigger legs means you can take bigger steps. It might even also mean that, for all of these numbers, the person's probably fully grown. But if I were doing smaller measurements, the really small legs probably belong to babies and toddlers, so they definitely would be running slower. But even for adults, if I've got longer legs, I'm going to have an advantage in terms of my top speed. Each step will take me a little bit further than someone with shorter legs. So I can probably get up to a higher top speed if I have a nice flat surface to run on. And something of that nature. So the line can be justified through a cause-effect reasoning. There is not simply some sort of correlation going on here. There's an actual causation occurring, and so the line graph is justified. If I were to instead draw bars like so, to basically I'm saying, well, I'm not confident there's a cause-effect relationship, so I'm just going to play it safe and draw bars instead. This is actually false because I'm not playing it safe. I'm actually making a statement. I am claiming when I draw bars that leg length does not affect your running speed. That is what the bars claim. And so you have to be able to justify that there is no cause-effect relationship if you're going to draw bars. So there's no safe option here. You have to think through your scenario and you have to decide, does a cause-effect relationship exist? Are the in-between values between the measured data points logically guessable or completely unknowable based on the experiment that you've run? And you have to make your determination based on that. Now, it's worth noting, even when there is a cause-effect relationship, so I'm confident that the curve that I've drawn here is justified, that doesn't necessarily mean that I can use this curve everywhere. For example, if I continue this curve out, it seems like it's getting bigger, 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 maybe slower. It might be what mathematicians call asymptotic. It's sort of becoming more and more flat as time goes on, even though it's continuing to get a little bit larger. And so I might conclude that someone who has legs that are 300 centimeters long is going to be the fastest runner possible. But is this true? Well, if a human, a normal biological human, was actually born with legs that were 300 centimeters long, and that human tried to get out of bed and support himself on those legs, he'd probably break his own legs. If you've ever watched a fantasy movie that has like giants running around, usually tossing boulders and smashing trees and like entire infantry troops being just like thrown to the side, the physical reality of a giant is a giant wouldn't be able to get out of bed. Human anatomy, with the ratio of leg diameter to height that humans possess, the legs would be crushed under the weight of the torso. So giants are actually one of the least scary movie monsters that you can think of, because they would just be bedridden invalids in reality. But they look cooler when you just ignore physics. So getting back to this graph though, if I try to take a curve that I have data for and extend that curve beyond my data set, the further I get beyond my data set, the less reliable the conclusions that I try to draw become. Because I don't know if, based on my data set, the reality is that leg length continues to result in continually faster speeds, or if there's going to be some critical length after which your top speed suddenly drops to 0 because you can't support your own body weight anymore. So for line graphs, a lot of times you can only trust, really trust, locations that are in between data points, like this area, or regions that are very close to where you've made your measurements. You can probably still trust that your conclusions are accurate for someone with legs that are 101 centimeters long. You just maybe can't extend that out to 200 centimeters or 300 centimeters. You get a similar problem if you go the other direction too. If you go the other direction, does this line just kind of keep going like this? Does the line drop down? I mean, depending on what the line does, interesting things could happen, right? I could end up with a scenario where if I extend my axis back this direction, and I assume that my curve kind of flattens out, this would be stating that someone who has legs that are 60 centimeters long cannot move at all. And someone with a 60 centimeter legs is going to be quite mobile. And if I go out to 50 centimeter length legs, well, that's even more ridiculous. I'm claiming their top speed is imaginary because they are going slower than stationary, according to this graph. If I assume that the curve kind of flattens out to form a straight line. So once again, we have this scenario where if I go too far beyond the end of my data, at first my data is trustworthy, my conclusions are trustworthy beyond the data range, but if I go too far beyond my data range, the conclusions that I might have become less and less and less trustworthy. They just become more and more possibly ridiculous. And it's not always clear where your data loses its validity. So you just have to be careful of that when you're dealing with line graphs. So that's line graphs and bar charts, kind of comparing them and what they're saying. The final one, obviously, to talk about in a little bit more detail would be something like a pie chart. Now, with a pie chart, if I have a scenario where I have a question that I'm confident that I've covered all the bases with my answers. For example, what kind of siblings do you have in your house? And so some people might say, well, I have brothers. Some people might say, I have sisters. Some people might say, I have both brothers and sisters. And some people say that I don't have any siblings, right? So in this case, at least if I'm only, talking about, straight up genetic biology here, there aren't, much in the way of other options. So I can be pretty confident that I've covered all the bases and all the wedges should add up to 100%. So pie charts work great when I am confident that everything adds up to 100%. Where pie charts are more difficult to use is if I'm doing something like trying to keep track of the budget of a city. Cities love to show their budgets in pie charts, but it's difficult to do that because you might know how much money goes to the mayor's salary, and you might know how much money was given to the water works department, and you might know how much money went to this department, that department, so on and so forth. At the end of the day, a city is such a complicated economic entity that there's going to be some money that was collected for taxes, and you can't figure out where it went. So you have this beautiful pie chart that seems to show everything adding up to 100%, but the numbers don't quite add up, and you can't quite figure out why. And so in this case, a lot of times what you'll see on a pie chart is you'll see a little wedge that is simply called other. And that is, basically a statement, sometimes the maker of the pie chart truly knows everything that's going into the other category, but sometimes it's simply a statement of this is what we lost track of. We know it exists, but we lost track of it. And obviously for a city budget, if you have an other slice that is, only 0.01% of the total city budget, you probably don't care. Probably that money went to some office party somewhere where it probably shouldn't have been spent, but it really wasn't a big deal. Or maybe some clerk forgot to record the paperclip order that they made one day or something like that. So, little side purchases might not have been recorded the way that they were supposed to. But if the other category is small enough, the auditors, taxpayers probably are willing to let it slide. If that other category grows to be 50% of the city budget, maybe it's time to open a corruption investigation, right? Uh, so pie charts, again, they're wonderful if you know what 100% looks like. So you can actually tell if your pie wedges that you've measured add up to 100%, or if you have a scenario where you're confident that you've covered all the possible categories, so you know there's no other category to even worry about in the first place. But in a scenario where you don't know what 100% is, and it's complicated, so you're not confident that you've covered all the choices, a pie chart's a very dangerous thing to use. You're probably better off sticking with a bar graph, and that way you don't have to worry about the size of the other category, because a bar graph doesn't claim that you're trying to add up to 100% in the first place. And this covers what I'm going to say about data display.